In this lesson, we will cover part 3 of electric circuits, which will go through EMF and internal resistance, and then we will move on to work, energy, and power. And this all forms part of the physics syllabus. So a circuit needs a source of potential difference to drive charge in the circuit. As we said in the previous video, we know that charge flows due to a difference in potential difference across a terminal. So it flows from one side of a battery to another, and that is due to potential difference across those two terminals. So the cell maintains a potential difference between 2 points so the charge flows. So as we said, the cell, being the battery, maintains a potential difference and causes charge to flow. Now EMF is the total energy supplied per coulomb of charge by the cell. So it's a total energy a cell can deliver. And remember that your cell is your battery or your source of energy. EMF is the voltage measured across a cell when no current is passing through the cell. So if you disconnect or you break the circuit, then EMF is the voltage measured across the cell. Now, we need to know about internal resistance. So we've looked at resistors in your circuits. Now we need to look at internal resistance, which is resistance within your cell. If a cell has internal resistance, then the EMF of the cell will not equal the voltage supplied to the circuit by the cell. Some EMF, which remembers your work done per unit charge, is lost within the battery as charge moves through the cell. All real cells have internal resistance. So to put that simply, we're saying that your EMF of the cell will not equal the voltage that the cell supplies, simply because some of that EMF is lost within the battery as charge moves through the cell. So if resistors are added or removed from a circuit, the current will be affected and the terminal voltage will be affected, but the EMF of the cell will remain unchanged. So no matter what, the EMF of a cell will always remain constant. So the sum of the voltage across the external circuit, as we see over here with V load, is your voltage across the external circuit, plus the voltage across the internal resistance, which is V internal resistance, is equal to EMF. So EMF equals our voltage across our load or across our circuit, and plus our V internal resistance, which is the voltage lost within our battery. And this is a formula on your formula sheet. So EMF equals I times R external plus I times R internal. So this will be your external voltage and this will be your internal voltage. This is simply by rearranging your R equals V over I to get V equals your I times R. So your potential difference of a battery, your V equals EMF minus your IR, because your voltage that's delivered to your circuit will be your EMF, your total EMF of your battery, minus the voltage that's lost inside your battery. So therefore your voltage equals your total minus what is lost. And if we plot that on a graph, we see that V external, which we're plotting on our y-axis, equals negative IR. So I is now our x-axis, plus EMF. So your y-intercept is now the EMF of your cell, and we see that with varying values, our V external changes according to our current. Energy. Then we move on to energy and power. So energy is dissipated in any electrical component. Our power of our cell is equal to our EMF times I, which is simply our V times our I, voltage times our current. So we've said that energy is dissipated in any electrical component. Now energy, we have these formulas on our formula sheet. So energy is measured in work is measured in joules, which is equal to V, which is your voltage, times your I, which is your current, times time. It's also equal to I squared, being your current, times your resistance, times your time, which is also equal to V squared over R times T. Now we look at the power dissipated in a component. So we know that energy is lost or dissipated in any electrical component, and we know that power is also dissipated in a component. Power, we know, equals W over T, and by rearranging the first formula over here, we get that power equals V times I. Remember, the power is measured in watts. Power is also equal to I squared times R, and power is equal to V squared over R. So these are combined to form equations. You will be given some of these equations on your formula sheet, and the rest of them you can derive from what you're given. Then they like to ask questions about the cost of electricity. So obviously electricity is charged in kilowatt hours, which is a unit of energy. So kilowatt hours is obtained by expressing the power kilowatts and the time in hours. To get kilowatt hours, you convert your energy to kilowatts and multiply that by the hours that you use your electricity for. So let's look at this example where we have a 60-watt globe that burns 6 hours a day for 31 days. So obviously we need to convert 60 watts to kilowatts. So we divide by 1,000, so it's 0.06. And we need to work out how many hours we've used it for, which is 31 times 6 hours, so 31 days and 6 hours a day. And then we simply multiply our kilowatts by our hours, and we get that we've used 11.16 kilowatt hours. Now they've told us that it costs 95 cents per kilowatt hour, so we simply multiply 11.16 by 95 to get it into cents. We then divide by 100 to get it into rands, and we see that it's 10.6 rand, so it's 10 rand 60 cents. Then we look at brightness and the heating effect in resistors. So we had a look at this in the last lesson, but we'll have a look at it again now. So the brightness of globes and the heating effect of resistors is directly proportional to the power that is flowing through these components. We know that brightness is directly proportional to the current that flows through the globe. And when we're solving problems relating to power, in parallel we use formula with voltage. So that's just a nice quick tip. And point 2, in series we use a formula with current. And if the circuit is altered by switches, we start our calculations again, because this will affect our external voltage, our current, and our total resistance. Remember that the only thing that's not affected by changing your circuit is your EMF, but your external voltage, your current, and your total resistance will be affected, and you need to restart your calculations. So let's look at this quick example over here, where we look at comparing the brightness of two globes. So if we have a series circuit, so in series current is equal to 3 resistors, we know that power equals I squared times R. So we know power from this formula is therefore directly proportional to your resistance. Now, the more power dissipated in your 6 ohm resistor, because you've said your power is directly proportional to resistance, so obviously less power will be dissipated in the 3 ohm than in the 6 ohm, and therefore your 6 ohm resistor will be brighter. So this globe would burn with a brighter light, because we've said that your brightness is directly proportional to your power. Now, when we look at parallel, so as we said, when we dealing with series, we deal with current. So we've used our current formula over here. And when we're dealing with parallel, we use voltage. So we look for a power formula that takes into account voltage. Now your voltage across your resistors is equal, and we now know that power is directly proportional to 1 over R from our formula. So the more power dissipated in your smaller resistor. So if so our smaller resistor, by this proportionality over here, will have more power dissipated, and therefore your 3 ohm globe will burn brighter. So in this way, you will always take your formulas, you will arrange it to suit the question that you're looking at, and we always get a proportionality statement where we can then compare the brightness in our circuit. Often they won't give you values, they won't ask you to calculate the brightness or the power. They will often ask you to do it theoretically, and this is the approach that you should take when you answer questions of this nature.